In this session, we will be discussing about inverse kinematics. The last session, we discussed about forward kinematics. So, what is forward kinematics? So, forward kinematics converts the joint coordinates to the Cartesian coordinate. That is, the using the theta value or the joint variables, either the theta or the prismatic joint variables, you will be determining the Cartesian coordinate, that is the position x, y of the end effector. The inverse of it, that is given the pose of the end effector, determining the joint coordinates, that we call it as inverse kinematics. So in this content, you will have what is inverse kinematic problem and the issues you have in inverse kinematics, and what are the different solutions for inverse kinematics. What is the inverse kinematic problem? So as I said now, so you will be given the this is the end effector pose. The end effector pose, which means the position and orientation, will be given to you, and from the, for that defined or desired pose, you should determine the different joint coordinates. So here, as you see, so this is known. So the end effector pose is known, and you have to determine all the joint coordinates. So how will you determine the joint coordinates given the pose? So if you are given, so if I say the transformation matrix or the pose of the end effector is known to you, then from the transformation matrix you can determine the rotation matrices, and also the that is a position information and the rotation information can be obtained from the transformation matrices. So from the transformation matrix, that is you will get the, using the transformation matrix, you will get this relation, that is forward kinematics, that is x is equal to f of q, right? So if you are given q, taking the inverse of it will be giving you the joint coordinates, right? Taking the inverse of the will be giving you the joint coordinates. So if you are having an object, say as stated here, so the object frame is denoted as O here, and this is the manipulator. So the base frame denoted by B, and the end effector frame denoted by E. So your objective is to determine the um, base, that is the transformation matrix B relative to the O frame, that is the transformation matrix of B frame relative to sorry, transformation matrix of the O frame related to the B frame, right? So that is the set. So in order to grasp the object, this transformation is desired. So first you need to know this from the base frame, what is the transformation required to reach the end effector frame, so that you can make the end effector frame transformation matrix and the object frame transformation matrix both equal, right? So we need to find the joint configuration Q to reach the object. So there are many difficulties in solving the inverse kinematic problem than for doing a forward kinematics. So the first is that it is very difficult to determine if at all there exists any solution to the to solve the inverse kinematic problem. So whether a solution exists in solving the inverse kinematic problem, that is a difficulty. And also, even if the solution exists, it may not be unique. So the solution may not be unique. It may have multiple solutions. Another drawback is that the inverse kinematic problem, it is actually the equation, it is a transcendental nonlinear set of algebraic equations. So solving those equations is very difficult. And supposing if you are to determine the, I mean, where for application where, or you have to design a controller wherein you need to just do a tracking problem, right? So for every no end effector position, you need to determine the joint configuration. So in that case, you want a very fast computation, as well as you need to also impose some optimization based techniques, so that the solution inverse kinematic problem or will be getting the solution in real time. So there are different ways to solve the inverse kinematic problem, like how we saw in forward kinematics. Here, inverse kinematics also you have two general approaches. One is the analytical method, and another one is the numerical method. So the analytical methods are very fast to execute, whereas the numerical methods are so time consuming. So if at all you want to apply in real time, so this numerical approach it is not preferred, because as you know, numerical approach, it is an iterative approach, and it will though it gives some solution, it is very time consuming compared to the analytical approach, right? So on analytical methods, on the other hand, it are faster to execute. Issues in inverse kinematics. So as I have started with there are many issues in solving the inverse kinematics problems. That is, it has solvability issues, or it has multiple solutions, and many more. So unlike the forward kinematic problem, so solvability issues. Say supposing if you are having some n degrees of freedom kinematic chain, and the inverse kinematic problem is to find the joint rotations or displacements, and you have to just determine the transformation matrix, say H, let 0 to n, right? So if the task space is m, right? So then m independent equations we need to find, so as to determine the n unknowns. So in order to find the n unknowns, you need to have m independent equations. So if at all m is equal to n, okay, if at all m is equal to n, you will get finite solutions, because the equations are non-linear. Therefore, one or more solutions to inverse kinematic problem, but finite number of solutions you will be getting. Whereas if m is greater than n, m is greater than n, as in the second case, so the number of degrees of freedom is not sufficient to account for all the possibilities of the position and orientation. So you may or may not get a solution. And in the third case, that is m is less than n, you will get infinite solutions. So the robot is said to be redundant in this case. That is, the degrees of freedom is more than it is required in order to provide the desired end effector force. Let us learn the solvability issues by considering this example. So it is a planar workspace. So in the first case, as you see, there is no end effector. So the first two links are sufficient in order to position, but the end effector orientation, to reach the end effector orientation, that cannot be achieved, right? So it has only 2 degrees of freedom just to position the end effector. And in the second case, that is m is equal to n, that is the degrees of freedom is equal to 3. Whereas in the third case, that is, it is a redundant manipulator with more number of that is joints, that is your degrees of freedom is 4 in this case. In general, for a manipulator to have all position and orientation solutions, the number of degrees of freedom should be equal to the number of unknowns. So that is, it must at least match the number of independent constraints. That is, n should be always greater than or equal to 6, right? So n should be greater than or equal to 6 so for any manipulator to have all position and orientation solutions. So multiple solutions, it is another drawback in inverse kinematic problem. So both the solutions are the same. Say for example, if it is the left arm, so the elbow up and elbow down, you have two solutions here. So both the solutions are the same and they produce the same configuration of the end effector. That is, the end effector configuration will be the same in both the cases, but as you see, the joint space is different. The joint angles is different in both the cases. So, say for example, you have two angles here, theta 1 and theta 2. So, this is elbow up and here it is elbow down, right? So, you have multiple solutions. So even in the second case, that is your elbow down, there is a possibility that the joint link, it may collide with any object that is lying on the workspace or the work table itself. So there is a drawback in this elbow down solution. So normally we prefer this particular configuration, joint configuration for the inverse kinematic problem.